Okay, we're in section 14. It's the introduction to sequences and series. Um, Notationally, you might be confused by some of the notation, but for the most part, you've been seeing sequences and series for some times. People confuse the words though, all right? Oh, before I say that, again, the structure is lecture. We discuss things, then we do examples, then you practice the examples, study the material, then you do the web assign in really that order, all right? Also something in the weekly discussion group if you can. All right, so, we'll talk about this. I'll go to the whiteboard. Again, for the students that may benefit by watching these videos, I want to encourage that. Watch the videos. If it helpful, if it's not helpful, don't watch them. All right, so we'll go through, these different types over here, explicitly defined terms or recursively defined terms, and we'll go through examples certainly. We'll also talk about a series. Again, we'll talk about the difference between the word sequence and series. We'll talk about notation, which some students get confused by. Again, over time, though, you'll be less confused by notation once you start to become familiar with it. You'll be less confused by it. So we'll go through some examples, and those examples that we'll go through, we'll do that after the lecture. So lecture is going to be short. It's not going to be a long lecture, right? And then what you do is we do examples to get across the points that we're trying to make in lecture. But you'll get a chance. And someone says, when do I get a chance? You'll always have a chance to work here. That's one thing about Essex College. We want you to work towards a goal, and your goal should be, becoming educated in certainly the field that you're interested in. But you'll get examples. These are supplemental activities. They're called homework. Yeah, you got to do work outside the classroom. You do that. After you finish that, though, you'll come back to WebAssign. And WebAssign should be very simple at that point. It should not be difficult. Just like when you take exams, if you studied, the exam should seem very simple. And likewise, when you start to move forward, like into another course, like for example, Calc 1, it should seem like a simpler class once you study the material. The problem for a lot of students, though, is that they don't get the base knowledge to move forward. And that's really heartbreaking when someone's at the calculus and they're confused by what's in OA 6 or something. It doesn't bode well for your futures. You need to study. And the key is, hopefully you have the time to study. So I'm gonna switch screens on you. Not only time to study, but to come to lecture and pay attention. And I'm going to go to my whiteboard. Okay, so where are we now? Just to remind you, we're on the sequence and series business. And we'll talk about the meaning of what a sequence is and what a series is. Some people have fixed ideas what they mean, but we'll talk about it more explicitly. All right. After we go through lecture and examples and you practice the material that we give you in your notes, do the website and do something in the weekly discussion group. All right, go to the next page. And I'm going to sort of when I say read, I'm not going to say read every word to you, but, I'm going to read, okay? Infinite sequence. Okay? So what does it say? An infinite sequence is a function having its domain a set of positive integers. So now we got some kind of function and say there's a function whose domain is the positive integers. This is the domain. And what would be the range? Well, the function takes these integers as arguments and returns the range. All right, it's an infinite sequence. All right. Okay, let's go to the next thing up. Finite sequence is a function having as its domain the positive integers. I got this over here, but it's finite. It stops somewhere, whereas the infinite one goes on forever. Again, what's its domain? A finite set of positive integers, 1, 2, 3, up to n. That's the domain. What's the range? Well, this function is going to take these numbers that are in the domain and return something in its range. All right. Now, the range doesn't say it's integer. It just simply says the range is some numbers. All right. So over here it says, although we normally talk about positive integers for the domain, it is often convenient to start with non-positive integers. Sometimes we start with 0. We like starting counting with 0. I notice when I travel the world, some people do start counting at 0. Other people start counting at 1. It depends. But you can count from other numbers too. For example, there are many buildings where the first floor, what I call the first floor, is -1. Yep, that can happen. We can start counting from any number, integer number. All right. So I don't want to confuse you with this over here, but for the most part, we're going to have this notation, all right, for our sequences. All right, let me talk about the notation for you. And as I go through this, I want to point out, I'm going to indicate the domain numbers. 1, 2, up to n. So what I'm going to claim over here is that this thing A, whoops, sorry about that. This thing A is a function of n. Whatever the term is A, it's a function of n. So let me point out what an is. An is a function. What's the domain of that function? N. What's n? It's a positive integer. However, we could talk about different integers, like starting at -1 or 0, or even starting at 7. All right? So I'm going to say it's basically just a function. It returns something. And what's that sequence going to be? A1, comma, A2, comma, A3, comma, A4, up to AN. If it goes on, it goes on. It's infinite. Some sequences do go on forever. Some just stop. Okay, how are we going to define our sequences? Well, we can do it explicitly, or we can do it recursively. I actually prefer explicit because it's really the most intuitive. So this is an example of an explicitly defined sequence. I'm going to write it down for you. So I'm going to write down A1. A1 is a function. All right, what's the function? It's the function of 1. How's the function determined? I'll write this down for you. I'm just copying. N is 1. What goes in the bottom? 3 times 1 squared. Well, that's 1 plus 1. There's a 1 there, sorry. Minus 1. See, what do you get in the bottom? 3 plus 4. That's not bad. I could write down A2, right? That's f of 2. What's that going to be? Minus 1 squared. Then it's going to be 3 times 4 in the bottom plus 1. What do you get over there? 1. Let's see, 3 times 4 is 12. 12 plus 1 is 13. Well, that's not bad. I can write that down. What's A3? I think you get the idea. I don't want to do this forever, but you could. Let's see, 3 squared is 9 plus 1. Well, the top number is minus 1. Well, what about this sequence, by the way? It kind of alternates. You know, it starts at -1, then goes to 1, -1. It's the bottom that causes trouble for a lot of students, though. 3 times 9 is 27. 27 plus 1 is 28. All right? If I were to write that sequence down, you could write it as a listing, -1/4, comma, 1/13, comma, -1/28. I'm going to say yada, 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 yada. All right? We can compute more terms, and we'll do that when we get to examples. All right? Let's go to the next one, recursive. Recursive means it's in terms of itself. So let's write this down. A1 is 5. Well, I see that. What's A2? It's still a function of n. So now what do I know? I know n is 2. I'm looking at the formula. We'll put the formula down. So what do you get on top? If n is 2, the top would be 3. But then the bottom is in terms of a prior term. And what's that going to be? A. Well, let's see. If n is 1, that would be n minus 1. So 2 minus 1 is 1. Do you know what A1 is? It's 5. Well, that was easy. Let's go to A3. It's still a function of n. What's n? 3. Well, what do you get on top? N plus 1. Well, if n is 3, you get 4. And bottom, what do you get? A. Well, see, it's 3 minus 1, 2, right? Do you know what A2 is? It's the prior term. So what do you have here? 4 divided by 3/5. I'm going to do the arithmetic. Sorry about that. That would be 4 divided by 3/5, which is 4 times 5/3, which is 20/3. Again, we'll do other examples. I was going to write the sequence down for you. The sequence is 5. The next is going to be 3/5. The next is going to be 20/3. All right, let's keep going. Let's talk about series now. We talked about sequence. Now we're going to talk about series. A series. Now let's kind of read it to you. All right. So it says, we will often add the terms of a sequence together. Well, we just did sequences. What are they going to do now? Add the terms together. Typically, it's called a sum or a series. So what's a series? A sum of the terms, right? That's not bad. Initially, we'll do this the old-fashioned way. What is that? One term at a time. 1 plus 2 plus 3, blah, 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 blah. All right? However, we need to get a speedier way of doing it. But let's worry about it. We'll add them together. There's a problem, though. So I want to let me put out this as an example. I'm going to tell you what the sequence is. The sequence is 1, 2, 3, 4, yada, 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 up to 100. That's the sequence. The series is 1 plus 2 plus 3 plus 4 plus yada, 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 all up to 100. Now, by the way, I don't think I want to add that together the old-fashioned way. So I'm going to talk about it. All right, I'm going to talk about this. 1 plus 2 plus 3 plus 4. I'm getting tired. Let me see if I can do this. I'm going to say maybe 48. We'll get there, right? Plus 49, plus 50, plus 51, plus 52. Oh, I'm getting tired. Yada, yada, yada. And let's keep going. All right, I eventually get towards the end. What was the end? It was 100, right? So I'm going to say 98, 99, and 100. Now, someone says you didn't write all the terms in. You're absolutely right. I didn't write them all down. There's 100 terms. There's 100 terms. 100 terms. No, whoops, I do not want to write down all those terms. It's too many terms for me to write down. What I want to do is I want to look at it. I want to see if I can do this. And the first thing I noticed, and this might seem strange to you, was that this one over here, I could commute it around and match it with this guy over there. And what would the sum of those two terms be? 101. And I could also look at these two terms, 2 and 99. And I think you could add those two terms together. What would that give you? Well, 101. And then I could take these two terms and add them together. And what would that give you? 3 and 98, 101. I think you see what I'm doing. Now, what would the next one be? It would be 4 and 97, which is still 101. I'll be ready to get 101, 101, 101. So let's take a look at the middle. This is tough. I know it's tough. We'll get there eventually, right? What's 50 and 51? It's still 101. What's 49 and 51? I'm sorry, I made a mistake there. I'll go backwards. I did 50 and 51, I got 101. I meant 49 and 52, so put that over there. What's 49 and 52? It's still 101. And I bet you know that 48 would go to 53. It's still 101. All right, remember the 100 terms. What I did pairwise matching. So how many of these would there be then? Remember, I did pairwise matching 100 terms. There'd be 50 of those. Well, it's going to give you 5,050. If you like, you take your calculator now, do 1 plus 2 plus 3, plus 4 plus 5, plus 6 plus 7. You get exhausted over time, 8, 9, 10. You eventually get to 100. And I guarantee you, if you didn't make any mistake in your calculator, that you get 5,050 on your calculator. It's really not that bad, all right? So we have a nice little formula now, and I want to kind of generalize it. And certainly when I generalize something, we'll get to mathematical induction. When I generalize something, I'm not really saying it's true. I'm just going to say it looks like it might be true. I just did one example. But if I took the integers from 1 to n, I'll write this over here. Again, you understand that n is an integer. I'm going to say it looks like maybe, looks something like this to me. And you might wonder where this is coming from. And we'll go through that. All right, let me take a look at an example. I generalized what I saw. I think I saw that. Who knows? Maybe I didn't see that. Maybe it's not true. But I'm going to do a simple one over here. 1 plus 2 plus 3 up to 10. And this one I could probably do without too much work. Excuse me. N plus 1 will be 11 over 2. 2 goes in 10, 5, 55. All right, let's see if that's true. All right, you know what I'm doing. 10 plus 1 is 11, right? And 2 plus 9 is 11. And 3 plus 8 is 11. And 4 plus 7 is 11. And 5 plus 6 is 11. And I got all the terms done. How many other? 1, 2, 3, 4, 5. Wow, 55. All right. I'm going to say pretty easy. Not bad. But again, you might be confused. If you're confused, take 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and you get 55. All right. We'll actually prove this formula when we get to PMI. What's PMI? The principle of mathematical induction. And that's very easy to prove, by the way. All right, right now, maybe you want to accept it. All right, let's talk about notation. And I know it's trouble. I do know it's trouble. All right, so I'm going to say we're going to talk about, I'm going to pull it on the side now. We're going to talk about this guy right over here. All right, we're going to talk about this guy. All right, one thing at a time. This letter here is from the Greek alphabet, and it's the letter sigma. I is a counting variable, and we're starting with 1. And we're going to stop at n. And then I'm going to say we're going to add together the AI. Remember, a is a function of the number, and they're integers. So what does this thing represent to me? Well, that sigma notation represents we're going to add together. So that we're going to start with I to be 1. Then we're going to go 1 to 2. Then we're going to go to 3. Then we're going to go to 4. And then we're going to go all the way up to the stopping number. Well, what's the stopping number? N. All right. So if I write this one over here, I equals 1 to 10 AI. What would I write down? A1 plus A2 plus A3 plus A4 plus A5. Yeah, it's work. Plus A6 plus A7 plus A8. Gee, I'm running out of room. Plus A9 plus A10. How many terms do I got over there? 10 terms. Let me count them up for you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 terms. All right, we're adding together. Now, someone says, I don't know what these things are. Don't worry about it. I don't know what they are either. We'll get there. All right, we'll get there. All right, so I think we covered that page. Let's go to the next page. All right, so let's talk about something that you may not be that familiar with. I got to put it down for you. An infinite sum. All right, and what I'm going to do is I'm going to put a little box in this over here, pull it on the side, and I'm going to talk about it. All right, I'm going to talk about this. Now, I'm going to say that some problems are really grade school problems, but you may not recognize that because of the way they're written. So I'm going to write the sum down for you. And again, you may not recognize things because of the way they're written. This says I equals 1 to infinity. Now, someone says, what does that mean? You start at 1, you go to 2, you go to 3, you go to 4, but you're never going to stop. If you're never going to stop, where's it going? It's going on forever. But each term is going to be of this form over here. So I want to write that down. So the first term would be 3 over 10 to the first power, which would be 10. The next term would be 3 over 10 squared. Well, that's 100. The next term would be 3 over 10 cubed, which is 1,000. Now, by the way, I actually believe if you write something down 3 times and you don't see the pattern, there is no pattern. But I know there's a pattern now. The top is always going to be 3. What's happening to the bottom? I'm just adding on another 0 each time. That's all I'm doing. All right. And how long does this go on? Forever. I'm going to write the decimals down for this, though. What's the first decimal going to be? 0.3. What's the next decimal going to be? 0.03. What's the next decimal going to be? 0.003. What's the next decimal going to be? 0.0003. I think you get the idea. So what I'm going to write down is I'm going to add them together. What would you get? 0.33. That's the first two terms. Third term, fourth term. I think you get the idea that this repeats itself over and over again. There's certain numbers you should recognize, and a repeating 3 is going to be 1/3. Let me just point out, well, you recognize that when you did that in grade school, 3 goes into 1. You put a decimal down, added a 0. You said 10. 3 times 3 is 9. Subtract, you get 10. 3, 9, subtract, you get 10. I think you get the idea. That's a pretty easy one. All right. So we did an infinite sum. Now, so when I say did infinite sum, we really didn't add an infinite number of terms together, at least not, one after another. We thought about it, and we've seen that before. All right. So that's a repeating decimal number. The 3 is repeating itself. Right. Turns out to be 1/3. There's many other forms of these numbers over here. Many. And we'll go through more examples of that. All right. So I think we pretty much covered that portion of the lecture. Of course, you might say, what are the examples going to look like? Well, they're related to the lecture, and we'll go through those examples, and then you're going to reinforce that by doing examples on your own. And of course, studying the material that we provide for you. Thank you.